Bartolomeo is a full professor of physical chemistry in the Department of Chemistry at the University of Torino. He received his degree, laurea cum laude, in chemistry in 1995 and his PhD in chemistry in 1999 from the University of Torino, discussing a PhD thesis on hydrogen bond in molecular and crystalline systems, an ab initio study, and that was under the supervision of Professor Uliengo. I hope I said it correctly. Right. It's difficult for a Polish person for some whatever reason. After his PhD, he spent a short period working with Professor Harrison at the CLRC Daresbury laboratory in UK. And then from 1999 to 2009, he worked as a postdoc research assistant at the University of Torino, first with his PhD father, on ab initio modeling of zeolites, and then with Professor Pisani and Professor Dovesi working on quantum mechanical methods to study perfect and defective crystalline systems, and that was from 2001 to 2002. And since 2002, he joined the theoretical chemistry group at the Department of Chemistry and of the University of Torino as a faculty researcher.
His primary research interests lie in the computational chemistry, with a focus on ab initio quantum simulations and applications of DFT in solid-state chemistry. He has been involved in development and application of the Crystal Code for many years and is one of the main co-authors of the latest release, Crystal 23. His contributions span both the theoretical implementation of the code's functionalities and the development of methodologies for its application to complex materials. He's an expert in modeling the bulk and surface properties of solids, such as microporous materials, example, metal organic frameworks, and molecular crystals. Recently, he has become intrigued by artificial intelligence and machine learning tools.
Bartolomeo has co-authored more than 180 very well-cited papers in excellent peer-reviewed international journals, with more than 25,000 of citations and the H index 66 according to Google Scholar. And I also want to add that many years ago, when we all were young, Bartolomeo came a few times to Warsaw, to our group in Warsaw as a visiting professor, and presented very useful workshops on the use of crystal for us and for our students and PhD students. And thank you very much for that, and thank you that you have agreed to present this lecture. Bartolomeo, the screen is yours.
Okay, thank you very much for the invitation, this very detailed introduction. I'm really very happy of this, a bit boring because I spent all my career in Torino, so nothing very exciting, but it's good to see and to be here. I'm very happy to take part in this webinar series, and I would be good to see you all in person, but I find that it's good also to have this online. So I'm really honored to be here today and to talk to you about our recent work. As Anya said, the title of the talk is really long, so I try to highlight the main keyword of this presentation. So what I will be talking about in the next slide, starting from the idea of what are large-scale calculation from my point of view, and then presenting what are the idea of composite methods implementing hybrid functional through the use of localized basic function as implemented in the Crystal Code. So what about large-scale calculation? Of course, in the last decades, there have been a lot of effort trying to move from small to medium and then to large and more complex systems are depicted in this slide from both molecular calculation. I will be talking about, of course, quantum mechanical calculation, but even for the solid state to reach the accurate results and be able to describe very complex systems. This is on a different point of view. Also, large scale means that we can also run a lot of calculation for large scale screening, for instance, for drug design or crystal structure prediction or high throughput screening. That this is very important now, when we need to create, to be able to have data available, for instance, for machine learning prediction and using artificial intelligence. Of course, the workhorse in the calculation in the last 30 years is density functional theory. And usually what we refer to are GGA or meta-GGA calculation, while it's now known that the inclusion of hybrid functional, the inclusion of three-focus change is important to improve the accuracy of the results from molecule to solids. So the point that I would like to discuss today, if to answer these two questions, are hybrid functional calculation affordable even for very large complex system and for large scale screening? And if we can do that not only using supercomputer, but also if we can do this in a cost-effective way, even referring to small-scale computing resources. So to do that, we need low-cost yet accurate method, and this must be combined with an efficient implementation. I will be talking about in the next slide. So the idea of composite method actually originates from Stefan Grimme, who some years ago proposed the combination of either RTFOC or DFT or the two through hybrid functional with minimal to medium size basis set in terms of localized basis function. So there means they are using atomic orbitals in terms of Gaussian type functions to describe large and enlarged system, particular at the molecular level. The idea is based on some error compensation, because using these method combined with small basis set, we can able to describe covalent system very well, and also medium range correlation. But as you know, DFT fails in describing difference forces, both at molecular level and for solid states. So one needs to describe non-covalent system to some empirical dispersion correction. So the idea that Stefan Grimme proposes to combine the DFT energy to three different corrections. This is why this method are called also 3C for this correction. One is for dispersive London dispersion energy. The second one is to take care of the basis set superposition error and the basis set incompleteness error through the GCP correction that are reported here. And then in some cases, also a short range bond correction is included. So these three or two terms are included to define the total energy of the system. So on the basis of this, he proposed a series or a hierarchical method starting from RTFOC to pure GGA and passing through hybrid functional to get good results for structure and also for energetic properties. These have been applied mostly for molecular and molecular depth, in some cases into molecular crystal, but actually was claimed that at that time that this was also available for the whole periodic table. So the point is that the method has been proposed at that time were actually not really capable of treating inorganic systems. So we start working on the extension and validation of these methods to inorganic and solid, inorganic solid and covalent solid, and also layered material and porous material like MOF that I'm going to show you in a while. So to do that, then we use our code, Crystal. So let me spend a few words about that, because this is based on the use of Gaussian type functions, so it's perfectly suitable to implement this kind of method. So Crystal allows to treat periodic system with different periodicity from crystalline solids to slab models, to polymer, up to molecule, running the calculation at the artifact level. That was the original method developed in the code many years ago. And then we introduced the density functional theory. Of course, it was easy to combine the two to have hybrid functional. And also the code is some peculiar features, like the full account of the symmetry, the full exploitation of the symmetry. And unlike other code for solid state calculation, we use a basis set of Gaussian type function that allows us to create a block function and then to describe the crystalline orbital as a linear combination of the block function. And from this, we can compute different properties. For the purpose of what I'm going to show you and the application of this composite method, is important to have an efficient implementation. And in this respect, Crystal allows user to run calculation with on different codes in a parallel way, not only in serial, with two different version. One is for replicated data that is based on either MPI, so we have now OpenMP, and with or we can use a distributed data way of parallelism to run calculation on very large supercomputer center, for instance, using 1,000 cores. That is this massive parallel version of the Crystal code called MPP. So what makes Crystal another peculiar feature I was talked to you about is the use of the implementation of an efficient implementation of hybrid functional due to the combination of Hartree-Fock and density functional theory through the generalized sham framework. In this respect, if we consider the Jacob's ladder, the code allows user to calculate and run calculation with the fourth rung of the Jacob's ladder, so from LDA to GGA, meta GGA, and then combine the three in where the Hartree-Fock is changed to have hybrid functional. And actually, the implementation of hybrid functional dates back to 1996 and was just a few years later with respect to the proposal of Becker of hybrid function. So we have hybrid functional since many years, and we have different flowers from which we can run calculation, as I show you in a while. So why is the code efficient? So let me just spend a few words on some technical aspect. This is the expression of the Hartree-Fock exchange that we have in the code. There are different summations that we have to take care, and also the calculation of the integrals. So the point is that using localized basis function as Gaussian type function, we can exploit the locality of the basis function in the direct space, so taking care of these finite summation over the orbitals, or also the more problematic infinite summations, and we can adopt screening techniques and different kind of to make this more and more efficient based on orbital overlap or the decay of the density matrix. So this means that the calculation of two electron integrals and the full SCF cycle is quite effective in our code with respect to pure GGA calculation. And here I just reported some recent results about the comparison of PBE with a hybrid functional, with the aim of showing how efficient is the code. And this is done with the bulk structure of hematite and a layered single layer of tungsten selenite. And you can see that the cost of the calculation from a GGA to a hybrid functional, including 50% of artifact exchange, but this doesn't matter very much for the efficiency of the code. Is just cost just 3 to 4, or let's say 4 or 5 times more than a pure GGA calculation. So in this case, this means that we have an efficient implementation of hybrid functional that can be used inside this composite method to arrive at creating hybrid composite method for solid state calculation. That is the aim of this, what I would like to show you. And so we did this and I would like to thank my collaborator, Lorenzo Na, who worked on this when he was a PhD student. And we defined a class, or a new class of composite method that we dub SOL3C because we refer to solid state calculation. And the method are mostly hybrid functional that employ exchange correlation functional device for solids like PBE sol. And we reduce the amount of artifact exchange that was used in the original method to have a better description of electronic and optical property of solids. And then we work on a more, probably the most crucial point, that is a revision of the basis set to adapt the molecular basis set that was adopted in the original 3C method to solid state calculation. So we end up, and then of course we readjust all the correction to refit the parameters in order to be consistent with the method and the basis set. So we end up in two methods, a global hybrid PBE sol 03C and a range separated hybrid at short range, that is HSE sol 3C. And we, as I'm going to show you in a while, we arrive at an accuracy that is comparable to triple zeta quality calculation, but saving a lot of time because the calculation now are more, the cost is for a double zeta quality basis set. Okay, so the first point is that we would like to answer is the question if our method gave the same accuracy as the original method that were originally proposed by Stefan Grimme. And here I reported the results for a data set of molecular crystal that is well known in the literature. Is called the X23. There are 23 molecular crystals with the structure at low temperature. And there are so nice results that are being also back corrected to take care of the thermal corrections to be able to have a direct comparison with theoretical calculation. So here I reported the results for the original 3C method and the new SOL3C method. And you can see from the mean absolute error or the relative Penzigen error on the volume for with respect also to triple zeta quality calculation at the bit relief level of theory and the cohesive energy. And you see that the error are really consistent within the method. So we didn't see any degradation of the result with respect to the original. So we have a method, we have the same accuracy, and the results are also comparable with a triple zeta quality basis set and also to other results that can be found in literature, particularly this PBE0, the complete basis set level. So the accuracy is more or less the same. So we have nice results that, and the other point is that can we really extend the calculation to solid state system like inorganic solids, covalent solids, and this is results for a set of 52 inorganic solids taken from this paper in which the author proposed what is called the POB triple zeta valence basis set. And we repeat the same calculation with our composite method, and we get results that are comparable with this triple zeta quality based calculation with respect to the mean absolute error, as you can appreciate from this picture, even if there are some tendency of this method to underestimate the unit cell value. But overall, the results are good. And we also have results that are in good agreement with the experiment for also for layer system and for other properties. I haven't time to discuss this. But this wasn't possible with the original method, so we were able to extend the capability of this method also to solid states. And we also tested the efficiency, and you can find more detail. I won't spend too much time on this slide. You can find the detail on this paper, but we were able to show the good scaling of the calculation, starting from system with 100 atoms up to 3,000 atoms, just running the calculation on small computing results containing 40 cores or up to 80 cores to arrive at the larger system with a scaling that is almost linear. So that shows us that we have nice results, good accuracy, good efficiency. So we can start thinking to use this method. We started thinking to use this method to large-scale calculation. And so since I've been working on metal organic frameworks more than 25 years, we decided to apply this to metal organic frameworks. For those of you who are not familiar with these materials, they are formed by an inorganic unit that is linked throughout space by an organic ligand to form a porous structure. And these kind of materials have been awarded with a Nobel Prize in chemistry just a few months ago. And they show this unique combination of structure and bonding. There are a lot of chemical versatility. There are more than 70,000 MOFs structure that have been synthesized so far. They show different size, large structural complexity due to the different secondary building units, topology defects. So are there really interesting materials to be studied, and they also show many different interesting properties, of course, from gas storage to catalysis and other. Okay, so just to show, I will show you some results. This is the first application I would like to show you if I have time. And well, the question is, how far can we go with studying this MOF? And these are very exciting results that we had applying our composite method in the study of giant MOF that contains up almost 4,000 atoms in the unit cell. You can see this unit cell is huge, is about 9 nanometer, the lattice parameter. And this is a comparison with the previous one that I showed you, this MOS5 with just 100 atoms in the unit cell. And we were running the calculation on very small computing resources, just 8 cores with a parallel version of Crystal. We were able to fully relax the structure with one of our composite methods, and we had these very striking results with the comparison of the predicted lattice parameter with respect to the experimental one. If you notice, this contains chromium inside, so this is an open shell system, very tough to be studied. And we also have, also from a computational point of view, and then we studied the interaction of carbon dioxide inside this material, and the predicted energy of interaction is in reasonable agreement with the experimental one, if you consider that this is a very huge and large system. So I will be talking about MOF later. The next step we took in the last few years was to move from to the next rung of the Jacob's ladder, considering a meta-GGA functional like the R2 scan, and we designed 2 different classes of new composite method based on R2 scan, one on pure GGA functional, and the other including some artifact exchange with a hybrid functional. But for this purpose, we also include 2 different type of basis sets device for solid. One is the DZP SolDev2 basis set, double zeta quality, and then the triple zeta quality basis set. So the idea of extending this to triple zeta quality is that this makes the calculation available from hydrogen to radon, because these have been devised for most of all the elements of the periodic table to allow us also to include lanthanides and other systems. So we apply the recipe that I showed you for these functionals, and we obtain a family of R2 scan based composite method that we started to apply and to validate, as I showed you before. So I will skip this part, and what I would like to show you is that having this new method, we were thinking to move to study to in more detail metal organic framework through high throughput screening. As I showed you before, MOFs represents an ideal playground for high throughput screening because there are a lot of structure that are being synthesized. There are also hypothetical structure. There are various databases available from which one can take the structure. So having available this cost-effective composite method, we can start running not only large-scale calculation in terms of the complexity, but also running more and more calculation to create ad hoc data sets that can be used for machine learning application, going beyond GGA and using hard-to-scan hybrid function for this purpose. So the two applications I would like to show you are the prediction of atomic charges and the prediction of interatomic potential. The first one is thanks to the work of my PhD student, Hera Paya. We started from a database that's called QMOF that contains 20,000 structure, and for which have been studied at the PBE level of theory, and they computed the DDEC charges, so they are available to be used. And we started from the DDEC charges to create databases in order then to select a small data set of system for which we can then run crystal calculation to compute Hirschfeld and Mulliken charges. So starting from the QMOF with a different composition, we selected randomly data set of MOFs from 500 to 3,000 MOFs. And then we also created a, let's say, chemically balanced data set of about 1,500 MOFs that contain an reported metal abundancy in the data set. So then we predict the charges of the atom through random forest or Hg bus with different chemical descriptors. And these are the results that comparing the randomly selected data set with this chemically balanced data set and these the QMOF, the whole QMOF data set for a validation set of 65 structure of MOF. And as you can see, this is the mean, this triangle is the mean error. And you see that this chemically balanced data set allows us to arrive at a very nice agreement with the whole data set of QMOF. So this means that selecting properly this data set allows us to reach the same accuracy in the prediction of the DDEC charges. So by using then this data set, we extend the calculation to Hirschfeld and Mulliken charges using our composite method as implemented in a development version of the Crystal code. And we get, again, a nice results in comparing these for this set of structure for this validation set, reaching an accuracy that is reasonable for the prediction of charges. So that was, I mean, like an exercise, but then we can use these charges to compute also properties that are interesting, for instance, for the simulation of the absorption of molecule through molecular mechanics. So we adapt a UFF force field, including our, for the electrostatic part, our machine learning predictive charges through RASPA code. And we started, this is one of the examples that we have, the absorption of CO2 inside a metal organic framework. And with the blue curve, we have the results that have been obtained in the literature with ab initio predicted the DDEC charges. And these fit very well and with matches with the predicted machine learning charges, and we get the same shape for the absorption isotherm, and also with the EFS charge that we predicted through machine learning. So this is a nice example of what we can do with large-scale screening. The next example I want to show you and talk to you about is the same kind of, let's say, workflow is we try to use these to select a small set of metal organic framework to try to create a machine learning interatomic potential, again, based on hybrid composite metal like this R2-scan0 POP3C. In this respect, we would like to go beyond meta-GGA function and see how it works. And instead of referring to molecular dynamics, trajectories, or other configuration, we decided to sample the potential energy surface by using the geometry optimization steps, because we selected a different set of MOF that contains almost all elements of the periodic table. So we end up with a large set of data to be used for the training the model, and we have about 5 million entries about atomic position, forces, and stress tensor, and this is being used through the MACE model, defining two different trained model from our data set. One is devised from scratch. The second one was fine-tuning of the MP0 data model, that is a foundation model that's been developed by the people who worked on the Chinese group for the MACE. So just to make the story short, I would like to show you the validation of this machine learning potential that we try to predict and accelerate the prediction of the structure of different MOF, and we refer to low temperature X-ray diffraction measurement taken out from the Cambridge structure database up to more or less 900 structure. And we compared the results with the MP0, a foundation model, and OMAT, two different foundation model for the prediction of material properties. And here are the results for the volume. So it is a macroscopic, if you want, properties. And we get very nice results with our trained model, derived machine model, with respect to the original, to the other two more universal, I would say, foundation model. And just to check if this was not by chance, we also look at the lattice parameter, and we see that the prediction of the lattice parameter is very good, in particular for this fine-tuned model that improve very much the results that can be obtained with the MP0. In these days, this work is in progress, and we are extending the data set to add more data in the data set and try to refine even more the model that we have devised so far. Okay, so that's all for the what about the application to metal organic framework. The second example I would like to show you about the application of this composite method is a more, I would say, fancy application that is related to predict the properties of materials that are no longer on the Earth but are on Titan. And in this case, Titan is quite interesting place, because the geological processes that occur there are similar to what happens on Earth, the precipitation, erosion, and evaporation. But the point is that the temperature is quite different, because it's about 90 Kelvin, and the material is also different, because instead of having rocks like silicate or aluminum silicate, we have organic molecules that are called cryominerals, and in particular there are co-crystals. So there are a lot of these co-crystals that have been studied recently by this paper, so we are attracted by this, and we try to study these different co-crystal. And the other point is, some of them are not longer, the structure is not available, so we started some work on crystal structure prediction using our composite method. In particular, I will show the results on this list of co-crystal that we study and there's evidence that are present in the atmosphere or Titan or in the lake that are at the surface of this satellite of Saturn. And we use our composite method to start to predict firstly the structure of these very simple crystals. So this is carbon dioxide mixed with acetylene, and we use specs with DFT B as work to run most of the calculation, but then we refine the results with our composite method, and we end up with a structure that is not unexpected because the packing is dominated by quadrupole interactions. And in this case, we try to compare then the infrared spectra that is very useful to compare to see and check if the structure is well predicted with respect to experimental data that have been published some years ago. And even if of course the peaks are not coincident with the one that we have in the experimental spectrum, because of we are running calculation at the harmonic level, if we look at the shift of the peaks that we can be observed when passing from the pure crystal to the co-crystal, we compute and we predicted more or less the same blue shift for carbon dioxide and the red shift for acetylene. So this means that the structure is well reproduced. So we compute the thermodynamical formation of this system, this co-crystal, with respect to the pure crystals, and we in this case we include all the thermal correction to arrive at the free energy. And in particular, we see that according to our composite method, there's some dependency respect to using double or triple zeta quality basis set. But of course, the free energy is really small because there are, of course, the packing is dominated by weak interactions. And there are also nice results about the fact that some of them are not stable. And this actually has been also seen experimentally. For instance, this carbon dioxide acetylene co-crystal is found to be unstable, and probably is present in the stratospheric ice cloud. And we see that this is not stable at each for the true level of theory. Okay, so this is just to show that these composite methods are also be applied to studying different systems ranging from metal organic frameworks also to molecular crystal. So going to the conclusions, I try to show you that using localized basis set, we can have efficient implementation of hybrid function. Of course, there are also other advantages when using localized basis function, but I won't take the time to discuss this. Then using the hybrid composite method, I showed you that they can have good performances in study different classes and structure and chemical properties of different solids. And they are suited then for application in solid state chemistry, physics, and I also added this quantum crystallography because I think this can be also useful for the community of quantum crystallographer. And the last remark is that then we can use this efficiently to run large-scale calculation on system, or large system, or for IEEE screening with this low-cost method. So I would like to thank all my collaborators that helped me in the last year to develop this method to run all the calculation for this application and machine learning tool as well, and all the people involved in development of the Crystal code, and also of course the project for funding. Finally, if you are interested in the modeling of moth, I'm organizing in collaboration with other colleagues at the University of Montpellier and Ghent a workshop that will be held at the end of August this year in Torino. So you're welcome if you would like to come and show your results about the modeling of moth. If you can refer to the website for updated information. And thank you very much for your attention.
Thank you, Bartolomeo. Dziękuję. Thank you, Bartolomeo, for this update of your new methodologies and fast methodologies.
I hope we have time for questions. I couldn't see.
Yes, so people are typing. While people are typing, I have one question. You mentioned the quantum crystallography. So, of course, there is my question here. You validated your method to show how well it reproduce geometry, the volume of the unit cell, and like geometry, the energies. Have you also looked at the electron density distribution? Have you validated it? Because it's a property which is rarely validated by people developing the method.
Yeah, sure. Yeah, that's a good question. Well, actually not. What we did is to try to test the method for predicting other properties. For instance, this is reported in the papers. We try to predict the vibrational properties, as you have seen, also piezoelectric and the electric properties of solids, but we didn't look directly at the density. The point is also that the idea of this composite method is to provide a fast method to get a good structure and accurate energies, but then this allows to have a good structure on which you can run a more, accurate, if you like to call it, a more accurate calculation with a higher level of theory, maybe increasing the basis set. At that point, you can use these to look at the density and get better results. So,
thanks. Yeah, that's a really good idea, actually. We have the first question from Martin Maździarz. Do you use pseudopotentials in DFT?
No, because of we are using localized basis set, most of the calculation we run out through are all electron calculations. Of course, we can use pseudopotential for every element, of course, but these are different from what are pseudopotential for instance, for plane wave calculations. These are used, to remove the core electron, simplify the Hamiltonian, then this effective core potential in the Hamiltonian, but it's to treat heavy elements. But usually we run the calculation, all electron calculations.
Anna?
So somehow I think connected to Paulina's question. So if you want to focus on electron density, this is a question that I hear quite often, and I want to have an expert's opinion. Do I optimize the geometry or not? And if I optimize, should I optimize the unit cell and atomic coordinates, or should I only focus on atomic coordinates, but there's no need to optimize? What is the expert's opinion on that?
Well, of course, my attitude is to run a full calculation. If you think about having, for instance, the exact method that you can use, your prediction should be exactly the same as experiment. Of course, we have approximation and assumption that limit the calculation and the accuracy of the calculation, but in principle, you tend to the exact results in some way that should be the experimental structure, for instance. Of course, one has to take all the thermal correction into account and everything. So if thermal, for instance, if you believe that thermal correction are really important, in some cases it's better to keep the unit cell fixed at the lattice parameter, as in, for instance, at room temperature, and then just re-optimize the structure. So this can help in some cases to mimic the thermal effects in a simplified way, if you like think about that. But otherwise you have to run a quasi-harmonic calculation, try to predict also the volume. But in principle, I would prefer to have everything consistent.
But in terms of polymorphs, for example, when you have, the energies, lattice energies of the polymorphs rather close, So I always wonder whether if I run the geometry optimization, whether I am still able to grasp the subtle changes between them, or maybe I am then too close to the global minimum and then I'm losing the information.
Hard question. Of course, no, I mean, in this case, what could happen is that, I mean, the systems or the polymers are similar in energy, but for instance, if you change the functional or if you change the basis set, then you get the energy difference could be even larger. So it's hard to answer your question.
So
I would keep the same level of theory
yeah.
and then trust on these and try to make the comparison. And of course, if you can improve the level of theory, that will be better, of course, to get better results.
Thank you.
Another question from Roman Gaida. What is the currently the upper limit of the number of atoms within the box unit cell, which we can calculate in reasonable time?
Well, it depends. What I showed you is we arrive at about 4,000 atoms for these MOFs that I showed you. Is so in principle we can run calculation on 1,000 of atoms in the unit cell. Of course, it depends. With this method, you can save time and using less CPUs for running the calculation. But if needed, of course, the MPP version of the code allows the user to run calculation on 1,000 cores. So at that point, you can increase the number of atoms in the unit cell. I think, we arrive at system up to 10,000, but just for testing the code. So I would say that, I mean, so this, if you would like to say it's the limit, I would say so, but 1,000, 2,000, 3,000 atoms in the unit cell, I think are affordable.
Just following this question, in case of MOFs, MOFs have huge pores. Do you fill them, or this is just empty space? And then
the MOFs, of course, are empty. Usually we refer to, I would say, cleaned structure. So we remove the solvent inside, but of course it depends what you are interested in. If you would like to keep the solvent inside, then you just can put the solvent molecule in the pores. An advantage of using localized basis set is for porous materials, you haven't to fill the voids, or like in for plane wave code. So in this case, we have atom-centered basis function, so the calculation is also more efficient in this for this class of materials. But usually we try to remove the solvent from the structure and to have remove the defects and just, of course, creating ideal structure. But that's just for, in this case, for validation or for creating this data set. But for application, of course, one can study defects inside MOFs or solvent or different species, solid solution, whatever you are interested in.
You're saying 4,000 or 10,000 atoms, so this is still too little for protein crystals with solvent.
Ah, okay. I see. Yeah, that's point. Actually, we have an application with a small protein, is cramping. And some years ago, a colleague of mine studied the crystalline structure of cramping, including also the solvent inside. He arrived at, as far as I remember, was one of the, in one of the first picture I show is this one. Let's go back. In the very beginning, it's.
Do you remember if?
Okay, this one is cramping with the solvent molecule inside. So, but cramping is 800 atoms, as far as I remember. So not a big protein. we didn't try after this test. We was just, interested to studying proteins, but we didn't try to apply crystal to larger proteins. But I think it would be doable. The point is to find the right structure with all the hydrogen, so it's not simple also to have a good structure. For Cranbane was nice because most of the hydrogen position have been identified through X-ray or NMR, as far as I remember. So it was simpler.
Mm-hmm. We have a question from Hans Bedbergi. Since you reported free energies, you must have an idea about phonons and heat capacities.
Yes,
have you tested some of your methods against atomic displacement parameters?
Good question. Not yet. We are collaborating with Anja Hauser, and we tried. We were trying with her to apply also our composite method for predicting the phonons and then ADPs, but we didn't. At the moment, the results are still very preliminary, so I can say that we tested this for ADPs, so that could be a good option.
Another question from Kanjun Chu. I'm sorry if I pronounce it bad. Does using the DFT functionals that you introduced today help us to use a basis set with diffuse functions?
Okay, the problem of diffuse function in solids is quite peculiar because there's solids are usually, in particular, if you look at the covalent system or inorganic solids, diffuse function could be critical for running the calculation. And actually, they are not important because there are a lot of overlap with all the other functions. So we don't need actually to have diffuse function in the basis set. Particularly if you have a dense material. If you have a porous material in some way, I prefer to talk about low exponent Gaussians with respect to diffuse function, because low exponents are around about 0.1 atomic unit for the exponent, or we can use even some smaller basis functions. But in this case, if you are looking for molecular crystal, these low exponent Gaussian function in some cases are useful, particularly to remove the basis set superposition error. But really, for instance, what are called augmented basis function are not applicable, and I would say a bit useless for modern solids, because there are a lot of redundancy, and also this could lead to linear dependency of the basis set.
And another question from Biswat Mohanty. Can localized atomic basis functions reduce numerical instability and electron delocalization errors in highly charged molecular systems?
I wouldn't say localized basis function. Probably for removing this delocalization problem, better. One can refer to hybrid functional, so including some artery focus change usually remove some self-interaction error and this delocalization problem that you can find in some systems. So that's the one of the main advantage of using hybrid function. But this can be obtained also when running a plane wave calculation, for instance, at the HSE level or with the HSE function.
Thank you. I do not see more questions or comments. So let us thank Bartolomeo for.
Okay.
Okay. We have one more question. From Łukasz Golan. Can Gaussian plane wave functions be used? Is there something like Gaussian plane wave function?
Not. This is not clear to me. I mean, mixing Gaussian and plane waves. There are codes that are both of them. I mean, like CP2K, they uses some plane waves and Gaussian too. But okay, this is not in the crystal code. I mean, the crystal is simply based on a Gaussian type function, so it's like a molecular code, like Gaussian or Gauss. So it's the same kind of approach. So I don't know if I answered the question, but.
Yes, thank you. I think that's maybe the proper answer. Yeah, so I meant plane. Okay, I meant plane waves like in CP2K. Yeah. Mm-hmm.
Okay. No, I mean it's a different implementation, so there are different algorithms.
Mm-hmm. No more questions, comments. Yes. So let us thanks once again, Bartolomeo, for really excellent questions.
Okay, thank you very much for your invitation, and